Towards the year 2000, technology is the most powerful influence in our daily lives. Tonight, we take a special look at the invention of the century, aircraft. This old military trainer is a symbol of the double edge of all technology, full of enormous potential for benefit and for harm. Since the earliest days of human consciousness, we've dreamed of being able to soar through the air with the birds, but we weren't able to do anything about it until this century, when two bicycle makers applied scientific analysis and a lot of practical know-how to build and fly the first successful airplane. It was the beginning of a new era. We took to the skies, and it transformed civilization, all within the span of a single lifetime.
The aeroplane. A story of dreams and genius. Inspired by an ancient longing for the freedom of the skies. The desire to fly like the birds has always been part of our myths and legends. The reality remains a passion.
I guess I fly because of the freedom. Being bird-like is almost like an out-of-body experience.
There have only been 29 X airplanes built. I'm looking forward to flying it, and I have all the confidence in the world that it's going to fly very well.
Doing a couple of loops and rolls is like taking 3 Valiums or double martini. It relaxes you and just, you feel good when you come down.
Gliding through the silence, David Harris is one who has at last mastered the winds.
And a lot of people think that you make the movements. Actually, what you're doing is shifting your weight so that when I move my weight to the side, it moves the center of gravity over to the side, puts more weight on this wing, less on that, tips it over. And then if I push out, push my weight back, that pushes the nose up and it carves the turn. I want to go fast, I pull in. Not pulling the bar in, but pulling my weight forward, getting my weight forward, lowering the nose, and the glider speeds up. Push out, reverse. My weight shifts back. The nose comes up and it slows down.
Perfected only in the 1970s, the hang glider brings a breathtaking intimacy to flying. Around the turn of the century, the glider experiments of two bicycle makers paved the way for the invention of the aeroplane. It took 5 years and more than 1,000 glider flights. The engineering genius of Wilbur and Orville Wright eclipsed the efforts of all their rivals. Starting almost from scratch, they designed and built their first powered flying machine, the Wright Flyer. Their achievement is recaptured by Ken Kellett.
Flying the airplane is just very, very scary. You lay in a prone position on the wing. It's uncomfortable. Your back is arched. Your left hand on the lever, which controls the canards in the front. Your right hand really just trying to hold your body up and balance you.
The canards controlled pitch up and down. They would also offer protection in the event of a crash. By moving the hip cradle from side to side, the wings could be warped to control rolling. This action also moved the rudders, so the flyer could be turned to left or right. Its first flight is recalled by the Wright brothers' niece, Mrs. Ivanette Miller.
I was 7 years old and in the second grade. That was on a Thursday. I'm sure I went to school that day. Nothing unusual happened until early in the evening before dinner when Aunt Catherine came to our house with a telegram saying the boys had flown.
The age of flight began in an empty field in Kitty Hawk, North Carolina. It was 10:30 in the morning, December 17th, 1903. With a toss of a coin, Orville won the right to roll into history. The first flight lasted only 12 seconds. The Flyer rose 4 times that day. On the final flight, Wilbur soared over 290 meters in 59 seconds. 4 years later, the first passengers could experience the new thrill of air travel.
Uncle Orv called on the telephone and said that he would take his 3 nieces up if they'd come out to the flying field. So all 3 of us went out on the interurban. We stopped at Sims Station where their flying field was. He gave the sign that he was going to start, and he revved up the engine and the propellers, and away we went. We sat on the lower wing with our feet braced against a strut. I looked out over the wings that were carrying us up, and the ground that was falling away. This was free, open flying, and there's nothing like it. Nothing.
Within the lifetime of Ivanette Miller, flying has gone from a risky adventure to an everyday experience. In 8 decades, her uncle's invention has transformed human existence. Today's airliners shuttle across the skies carrying more than 2 million passengers every day. There are some 600 airlines catering to the nomads of the jet age. They can whisk us across the planet in hours instead of weeks or months. From computers to cocktails, the demands of the air travel industry ripple through society. The jobs and revenues from the handling of passengers and freight to the manufacture of aircraft have transformed the global economy. After oil, air transport and tourism combine into the world's most lucrative economic activity. In North America, there are more than 250,000 civil aircraft. Thousands of crisscrossing flight paths create potentially hazardous rush hour traffic. Traveling up to 900 kilometers per hour, the planes on these aerial freeways must be radar monitored. Constant tracking on this electronic web allows air traffic controllers to safely direct hundreds of aircraft each day. The controllers form only one of the tribes of support and service personnel that have grown with the airline industry since the pioneering days. The first airlines were founded in the 1920s, some by former fighter pilots like the Canadians Bishop and Barker. This was the barnstorming era, when flying was more of a sideshow than a serious business. The daredevils thrilled and bewildered the crowds at the county fair, and occasionally they showed why they were called barnstormers. Aircraft also demolished natural barriers. Oxygen masks allowed the first flight over Everest in 1932. 4 years later, Wiley Post circled the globe at 10,000 meters. But the world first grasped the aeroplane's practical and economic potential with Charles Lindbergh's epic flight of 1927, when he crossed the Atlantic non-stop from New York to Paris. In remote areas like Canada's north, aircraft became indispensable to wilderness exploration. Within a decade of Lindbergh's flight, huge Empire flying boats built bridges between the continents. By the end of the 30s, these flying hotels carried passengers and mail on regular schedules across the Atlantic and Pacific. In scale and luxury, they mimicked the stately ocean liners they had begun to replace. Air travel became truly economical in the late 30s with the arrival of the Douglas DC-3. Safe, reliable, and efficient, the world's first Airbus. Some 13,000 were built, and hundreds are still flying today, more than 40 years later. In 1949, the age of jet travel was launched by the de Havilland Comet and the Canadian Avro jetliner. Twice as fast as the DC-3, jets would come to hold the edge in reliability and safety, as well as comfort and economy. The demand for air travel has fueled constant innovation. Today, the Boeing 767, a totally computerized aircraft, stands at the leading edge. Captain Duffy Dwyer.
What is really different about this aircraft is that we fly it almost entirely in an automatic mode. And it really differs from most other aircraft in the commercial fleets of the world, mainly in the use of the flight management computer, which is this unit here.
Codes for the Toronto airport and the destination in Miami are entered into the flight management computer. The airports are displayed along with navigation beacons, creating an electronic road map of the flight path. Once programmed, the computers can fly the entire trip from takeoff to touchdown, freeing the crew to monitor instruments and flight safety.
Normally there was another pilot who sat at a panel and he monitored various systems that were displayed on this panel. And he's been replaced by an electronic monitor.
While keeping track of the aircraft's systems, the computer selects a flight path that is the ideal compromise of speed, comfort, safety, and economy.
So on a typical takeoff, I would advance the throttles about an inch, and the throttles would automatically adjust to the correct setting for takeoff power.
At Seattle, Washington, the 767 is manufactured in the world's largest building, the Boeing assembly plant. It takes 6 months to orchestrate the assembly of more than 3 million parts. While much of the work demands deft fingers and skilled human judgment, most of the dreary, repetitive jobs are done by robots. Here, thousands of rivets fasten the aircraft's metal skin to the frame of a wing. In the manufacture of high-performance airliners, safety and reliability are the dominant concerns. Soon, each of these empty hulls will hold hundreds of lives. Before it goes into production, a new aircraft undergoes a myriad of tests. Tests to check how a punctured fuselage will withstand sudden decompression. Tests to measure its floor strength in a crash landing. Such tests are often spectacular. In 1985, a Boeing 707 airliner was filled with mannequins and monitored through a drop of 600 meters to test a fire-retarding fuel additive. Fires following crashes are often fatal to passengers who live through the impact. This rack simulates the tortures of flight. The 767 survived twice its designed lifetime, the stresses of 100,000 takeoffs and landings, with no sign of mental fatigue. These tests, along with constant monitoring and maintenance, help make air travel one of the safest forms of transportation. Over its 20-year lifespan, this 767 will fly 50 million kilometers and carry 3.5 million passengers. It looks like a dragonfly and sounds like a flying chainsaw. For thousands of hobbyists like Michael Robertson, pocket-sized microlights seem to have answered the dream of domesticating the aeroplane.
Microlight is constructed of really space-age materials. We have a Dacron sail, aircraft tubing, and hardware. This king post and wire system that this particular aircraft uses are especially effective in weight-to-strength ratio. That is, for a very light weight, it's incredibly strong, about 3 times as strong as a regular airplane.
They're built from easy-to-assemble kits that run from a few hundred to $10,000 a piece. In North America alone, there are some 20,000 of these flying lawn chairs. But that's still a long way from a plane in every garage. Oshkosh, Wisconsin. For aviation fanatics, the world's biggest love-in. They come here once a year in the hundreds of thousands. They come to fly planes, buy planes, or just to see planes. At Oshkosh, aviation's traditions are preserved with extravagant enthusiasm.
My name is Don Dobeck. I'm a manufacturing engineer at Western Electric Company.
I'm Wally Braun, civilian life. I'm Deputy Fire Commissioner in the Chicago Fire Department. We've probably spent at least 6 months getting this bird ready to fly, doing a lot of the rebuilding on it.
Dave came up to me at work one morning and with a clipping from the Sun-Times, and there was a telephone number to call for more information. So he called and we got involved, and a couple of months later we raised the money to bring this bird over from England. It had been recently acquired from the Spanish Air Force. And that was the beginning of the end. From then on, it's been work and fly and camaraderie.
My name is Chucky, and we flew in the B-17. We keep our B-17 down in Fort Worth, Texas. My husband found it at Dothan, Alabama. It was used for spraying fire ants. And he just couldn't resist having to have a B-17. And so he flew it home one day. When we do fly, our cost breakdown is about $1,500 an hour to operate. We burn about 200 gallons of fuel per hour, and we burn also 8 gallons of oil per hour.
When this plane was delivered to the Army, I was 11 years old, and I had 3 uncles that were flying them. And I said if I ever grew up, I wanted to have one. The airplane is a Boeing PT-17, used in the Second World War as a primary trainer for pilot training. We bought this particular plane 4 years ago. It was a crop duster for 27 years. And my wife, my son and daughter and I restored it. We just like to keep the darn things flying. You don't see very many anymore. And we're a little bit proud of it. And, that's half the fun of owning the darn thing, is sharing it with somebody else.
World War II Mustangs. Spitfires from the Battle of Britain. For 7 days, history thunders past. The aircraft that trained most of the Allied aces of World War II. These Harvards are more than 40 years old. This airborne revival meeting is not just a celebration of the past. Oshkosh is a mecca for the committed. Many of the spectators here devote all their spare time and energy to designing and building their own planes.
I built this airplane from plans. There's no parts available. It's not a kit. And the aircraft took 8 years to build part-time. It cruises 180 miles an hour, and it brought my wife and I to Oshkosh from Seattle in approximately 13 hours. And it was a fantastic flight, and we just love the airplane.
Some of these projects take years, and you can put this together in 6 months.
Yeah.
And when you put the last rivet in, you can go flying because you don't have to stop and paint it, dope it, put fabric on. You just get in it and go.
We're really happy with it. I mean, it's everything they said it would be, which is really strange because, you know, you make something, it never turns out that way.
So you bought this as a kit?
Yeah, it's called a kit. You get fiberglass, you get resin, you get foam, things like that, but you've got to actually create it.
Was it like a manual or something that you...
Oh, you get it's great. Yeah, it's a big book.
So they tell you
They
step by step.
tell you. They do. They actually
Take the paintbrush out of the
literally, they say, you know, with your left hand do this, with your right hand do that.
Requiring at least 1,000 hours of work, building this plane is not for the faint-hearted. Although it demands no special skills or tools, the final cost could run from $6,000 to $14,000. The plans alone are $200. When it's completed, it will be a Rutan Long Easy. It's made from styrofoam, fiberglass, and epoxy resin. Rutan designs are part of a revolution that is changing the shape of aeroplanes. The winglets on the nose of the aircraft are canards, once used by the Wright brothers, now revived to make Rutan aircraft safer and more stable than conventional aeroplanes. Extra stability also comes from the tip sails fitted to the wings. Designer Bert Rutan.
The most common fatal general aviation accident is the maneuver in which the pilot turns too sharply to line up on the runway for landing and stalls at low altitude and thus enters a spin or loses altitude and flies into the ground before he can maintain control and climb. These airplanes are relatively immune to that in that if they get too slow, they can still just complete the turn without the stall.
In a water tunnel, colored fluid simulates the flow of air over the cross-section of an aircraft wing. As the wing angle increases, the smooth flow over the top eventually becomes turbulent. The wing stalls, losing lift, and the aircraft drops. In Rutan designs, the canards in front are set to stall before the main wing. As the angle of the aircraft increases, the airflow becomes turbulent. The canards lose their lift and stall first. When the canard stalls, the aircraft pitches nose down, lowering the angle of the main wing. In this way, the canard prevents the aircraft from reaching a dangerously high angle and stalling completely. This effect is called stall limiting. It makes the Long Easy almost foolproof. In the world of aviation, Bert Rutan's designs have become legendary. Safe, lightweight, and economical, the Long Easy can fly almost 4,000 kilometers on a single tank of gas. The Voyager. This is Bert Rutan's most spectacular design. As it slips through the desert air, the Voyager prepares to meet aviation's last major challenge. It's designed to fly around the world, 38,000 kilometers, non-stop, without refueling. Rutan's concepts will be put to the ultimate test. Slender and willowy, the aircraft's low weight and high strength require a minimum of power. Empty, the Voyager weighs just over 400 kilograms. When fully loaded with fuel, it will weigh more than 10 times as much, some 5 tons. The pilots for this 2-week ordeal, Gina Yeager and Bert Rutan's brother, Dick.
This is basically what the airplane is constructed of. And it's a very thin, high-strength magnemite graphite facings on one side and the other. And in the center, it's a low-density honeycomb core. And actually, this type of advanced composites is really what makes this mission actually possible. Now, this honeycomb is made out of paper, and it's bonded. And I'll just peel it apart here. You can see that it's very porous, and it's very strong. Actually, for every square foot, it's about less than 1/4 pound. This is the space-age material, and this is the material that airplanes are going to be made out of the future, and not aluminum anymore. And although carbon is as stiff as steel, there's still quite a bit of flexing in the airplane. That's why the airplane needs to be span-loaded with fuel as much as possible.
It will take about 13 days to circle the globe. For the crew, it's a physical as well as a technological challenge.
The doctor will be working with us on the compatibility in the airplane with the fatigue noise fatigue and other factors in the program. There's some psychologists that will be working with us and helping us with the circadian rhythm, which is the same thing as the jet lag that will offset our schedule. When we're not flying, one of us will be in the back area, the sleeping area, and we'll be off duty. We'll either be asleep or we'll be taking down data.
It's a technical achievement. That's kind of the business we're in, so why not?
Starship One. With this design, Rutan's innovations shift from the world of the hobbyist into a billion-dollar market. As the prototype of a new generation of business aircraft, the Starship's safe, high-speed, long-range design is 30% more fuel efficient than its more conventional rivals. For the boardroom set, the Starship is the shape of things to come. The Thunderbird's aerobatic squadron in ceremonial war paint. They pirouette through the sky only meters apart. F-16 fighters, beautiful and deadly. Faster than 600 kilometers per hour, this geometry is totally unforgiving. Within a decade of the Wright brothers' flight, armies had found a new weapon and a new realm to fight in. During World War I, flying machines went into mass production as nations fought for domination of the skies. At sea as well as over land, aircraft changed the face of warfare. During the 1930s, carrier-borne aircraft began to replace the big guns that had dominated naval battles since the time of the Spanish Armada. In 1940, the Royal Air Force fought the Luftwaffe and forestalled invasion by the German Blitzkrieg. The Battle of Britain was the first to be fought and won entirely by aircraft. As machines of rapid deployment, air transports could move armies to remote battle zones in a matter of hours. In 1944, long-range bombers brought devastation to cities that would have been left untouched in earlier conflicts. B-29 swarmed over Japan to finish a long and bloody war. Two atomic bombs, a year of firestorms and incessant strafing left hundreds of thousands dead and 9 million homeless. War's deadly impetus for innovation produced the jet engine, first in Germany in 1938, then in England in 1941. Although scarcely a factor in World War II, the turbojet would soon dominate military aviation. Light and powerful, the jet engine has permitted the design of fast, versatile aircraft like Britain's Harrier jump jet. One of the secrets of the Harrier's success is its lightweight construction, using advanced composite materials in place of metals. Sheets of carbon fiber are cut into patterns by automated knife blades. These techniques are borrowed from the garment industry. Similar to materials used in Rutan's Voyager, these composites are lighter than aluminum, but stronger than steel. As many as 40 layers of carbon fiber are laminated in a pattern tailored to produce stiffness and strength in any desired direction. The laminated sheets, once molded to the aerofoil shape, are heated to permit bonding. Some of the tools look disarmingly primitive. The entire upper surface of the Mark II Harrier's wing is made from composites. Carbon fibers have created new life in an industry where the time from the drawing board to the scrapyard is often remarkably brief. With its ability to land and take off vertically, the Harrier fills a highly specialized niche. It can operate from small carriers and doesn't need an airfield, making it ideal for warfare in remote places. Today's fighters have to be able to undertake a variety of combat roles. The CF-18 Hornet is the latest acquisition of the Canadian Armed Forces. Colonel Al Duquetteville.
It's going to embrace all the combat missions that a fighter aircraft can possibly be involved in, and that'll be air intercept, air-to-ground tactical aviation, and air combat maneuvering.
Propelled by 16 tons of thrust, the F-18 can fly at almost twice the speed of sound. It's been acquired to match the supersonic bombers of the Soviet Union and to serve in Europe as a counter to the air and ground forces of the Warsaw Pact. In spite of its complexity, the F-18 is surprisingly easy to handle, but it could not be flown, built, or designed without the aid of computers. CADDY, Computer-Aided Design and Drafting, is used to design a new rib for the wing of an F-18 in the McDonnell Douglas factory at St. Louis, Missouri. The computer recommends the type of material to be used, its dimensions, and shows how and where it is to be installed in the aircraft. The design of an F-18 with its thousands of parts requires a data bank containing millions of facts, figures, and specifications. At McDonnell Douglas, this information is stored in the world's largest computer center. It is used to draw plans of the F-18's components and to provide the design data which programs the numerically controlled machine tools which shape them. These robots are capable of machining with speed and accuracy beyond the capacity of traditional craftsmen. Human skills in this industry are mainly involved in quality control. It's only in the final assembly that human hands are put to work. To date, some 2,000 F-18s are on order, but they're not recommended for impulse buying. Each comes with a price tag of about $25 million, about the cost of 400 World War II Mustangs. The F-18 is packed with computers and microprocessors to fight in all weathers, by day or night. Armed with cannon and missiles or bombs, it can strike with deadly accuracy. Mastering these avionics and weapons systems requires months of training. In a flight simulator, the aircraft's controls are linked to a television camera which passes over a model landscape to create an illusion of flight in the simulator cockpit. Models of potential enemies are scanned separately to appear as specks on the screen. As a map of the ground unrolls between his knees, the pilot maneuvers the F-18 until his radar locks onto the target. He selects a Sparrow long-range missile and fires. Real Sparrows cost $250,000 each. But in this ultimate video game, an invisible enemy can be destroyed without firing a shot. At nearly twice the speed of sound, this 20-ton killing machine twists through the air with hypnotizing grace. But without onboard computers, it would be impossible to fly. With their aid, the pilot can fly the F-18 to the limits of its performance without knowing where those limits are. In battle, he can concentrate on the complexities of combat rather than the skills of flying his aircraft. It's the arms race which defines these frontiers of innovation. This NASA spin test will define the safe limits of a new jet trainer, while supersonic wind tunnels simulate sustained flight at 2,500 kilometers per hour. And lasers permit minute analysis of the airflow over an experimental aerofoil. In the wind tunnel, innovations can be explored without the financial risk of building the real thing. But eventually, these simulations have to be tested in real aircraft, often at great human risk. In 1947, Chuck Yeager rode the X-1 rocket plane to become the first human to fly faster than sound. The 50s and 60s were heydays for experimental aircraft of bizarre design. This is the X-3. By 1967, the X-15 had soared to 100,000 meters and flown at 7,000 kilometers per hour, 6.5 times the speed of sound. Designed for hypersonic speeds on the edge of space, the Dyna soars advanced understanding of aerodynamics during atmospheric re-entry through temperatures of 3,000 degrees Celsius. Extravagant defense budgets gave us this high-altitude supersonic bomber nobody wanted, and the Blackbird spy plane, the world's fastest jet aircraft. These are technological marvels, but outside the wars they are supposed never to fight, it's hard to find uses to justify their huge costs. Some research planes are true exotics. The Scissor Wing tested a new but unsuccessful form of variable wing sweep. HIMAT was the last word in model test planes. Flown by a ground-based pilot and tried with a multitude of wing shapes, it explored extremes of maneuverability under electronic control. With swept forward wings and canards, the X-29 is the first X-craft to be built in a decade. Its revolutionary shape is designed to give it the maneuverability tested in HIMAT, the snappy agility needed to aim missiles more accurately and more rapidly. Swept forward wings also allow the X-29 to use less power than its predecessors, while flying faster and remaining in the air longer, always a crucial factor in fighter aircraft whose combat endurance is often measured in minutes rather than hours. The advantage of swept forward wings has been known for decades, but they tend to tear off at high speeds. Reinforced with the new high-strength, lightweight carbon fibers, the wings of the X-29 are made to avoid such catastrophes. The unprecedented agility designed into the X-29 makes it so inherently unstable it can only be flown through computers. These were first tested with small models in NASA wind tunnels. The X-29 is controlled through digital fly-by-wire. 3 computers interpret the pilot's commands and relay them electronically to the aircraft's control surfaces 40 times a second. Without these adjustments, which make the X-29 so stable and yet so responsive, it would be fly-by-prayer. The X-29 would tumble out of the sky and disintegrate in seconds. With its computers, canards, forward-swept wings, and electronic nervous system, the X-29 is a radical challenge for its test pilot, Chuck Sewell.
I've been involved with the testing of the airplane for about 2 years now. We've flown it many, many hours in the simulator, developing the flight control system and looking at the handling quality.
The X-29's maiden flight had the atmosphere of a space shot. On the ground, 130 engineers monitored every move and awaited the outcome. Planning has been meticulous, but there are no guarantees. The burden of proof rests with the test pilot, his 33 years of experience, and his knowledge that of his 800 predecessors, more than 100 of them were killed by their machines. In December 1984, the investment of 8 years of research and $140 million paid off. The X-29 took off to explore the frontiers of flight, to advance aircraft design, avionics, and the science of new materials. The sinister offspring of this aerodynamic embryo will be tomorrow's advanced tactical fighters, just a part of the arsenal science has sold us for a crippling price. Once again, we've reached the pinnacle of inspiration in our search for more elegant, efficient, and costly ways to kill each other. Through intensive research, an invention that has brought the world closer together has evolved into this sobering paradox. It seems a long way back from this war toy, this supersonic dart, to that awkward first flight on the sand dunes of North Carolina. Beyond the dilemma of knowing how we can use our knowledge, beyond the nightmare of knowing what will happen if we misuse it, survives the dream of those who can at last hang on to the wind.
Join some of the world's leading scientists for a fascinating look at what's beyond our world on part 2 of The Great Space Race, tomorrow at 8. Now stay tuned as Whoopi Goldberg invades Comedy Tonight next.